Hello, good afternoon, or good morning, or good afternoon, good evening, everyone, depending on where you are. Thank you for joining today's webinar. Today, we have a very interesting presentation about how OpenEO enables Earth observation at scale in the Copernicus data space ecosystem. A couple of housekeeping points, however, before we begin. We will have a technical presentation followed by a Q&A session at the end. You are invited as a participant to submit questions at any time using the Q&A panel. So if you go up to the top of your screen, you should see at the top a Q&A tab, which you can use to ask a question directly, and we will address those questions at the end of the presentation during the Q&A session. Please note that you will remain muted throughout the presentation, and you won't be able to take the floor. You will have no possibility to take the floor. So just a little bit of background. I don't want to spoil all of the surprise of the presentation before we begin. But as many of you know who work with Earth observation data, as these data sets grow in scale and in complexity, you as users face challenges linked to storage, compute capacity, and also the data sets being operational at scale and being scalable. So today's webinar actually is going to explore how cloud-native processing approaches on OpenEO within the CDSE, the Copernicus data space ecosystem, can help address some of those challenges. So today's speaker, his name is Victor Verhaert. He is remote sensing data engineer at Vito, and he's going to present today's topic. So Victor, I'll go ahead and hand over to you. The floor is yours.
Thanks, Evan, and thanks for the lovely introduction. So indeed, my name is Victor. I am a remote sensing data engineer at Vito, and largely involved with processing using OpenEO in the Copernicus data space ecosystem. I think roughly for the past 2.5 years, I've been supporting large-scale projects into scaling up their algorithms and being able to produce these pan-European or even global maps and data sets. That's really where my expertise lies, and I hope today during this webinar I'll be able to share some of this expertise with you. A quick overview of what I'm going to talk about. Some of you might already know OpenEO or CDSE. Some of you might never have heard of it. I hope the former is true. But either way, I'll give you a quick introduction into what both of those are, why we need those, what the problem really is, before we really dive into how we can scale it up. The target of this webinar is really how to scale up these OpenEO process graphs. So I won't go too much into how you can build them yourselves, but I'll give you small hints throughout the webinar as well on where you might discover how to do this yourself. After giving some OpenEO large-scale examples, I'll dive right into a do-it-yourself, a practical example, a notebook you can run for yourself so you can reproduce everything I'm telling you now. And as Evan said at the end, we'll have some time for questions and answers. So as we all know, there's quite a lot you can do with remote sensing data. We can do land classification, crop type classification, we can monitor disaster events, we can look at clouds, of course, often or not, you don't want to look at clouds, you want to look at the land beneath it. But there's a whole spectrum of things you can do with those with remote sensing data. But there's quite a lot of challenges you will face trying to implement these algorithms, these workflows. And the first one is, of course, each day there are terabytes of data that are added to the vast majority of data already present. Each day there's quite a lot of acquisitions from satellites, and the amount of data we can process is growing by the day, by the second almost. And that can be quite overwhelming. Remote sensing is an area of data engineering where the amount of data is really very large. And all this data is spread across different backends, different providers. Some might be at Amazon, some at the Copernicus data space ecosystem. And as a user trying to combine these different data sets, it might get difficult trying to access them all, getting the different API keys. And there's a lot of headache starting from those challenges. as well as once you have access to the data might be in different data formats. Some might be GeoTIFFs, NetCDFs, the new ZAR format. And as a user, you also need to have the right tools to manage all these different formats. So that's quite a lot of overhead for a researcher to do. Then let's say you got access to the data, you were able to load in the formats, you were able to produce your algorithm on a small scale. You might face a challenge of how can I scale this up? I might have processed this small area here in Belgium where I know the area pretty well, and now I want to prove how it performs at a full European scale. You might consider buying 10 laptops and letting them run for a few weeks in your office, but of course, everyone knows here that that's not really an option. And for these being able to process these vast amounts of data, you're going to have access to cloud processing or to have access to large clusters. And then I don't know how many of you ever received a code snippet from a colleague or anything, or anyone saying, oh, you should be able to run this, and then you have quite a lot of problems with setting up the environment. Perhaps Conda is not correctly installed, and then trying to install GDAL is a whole different level of headache, perhaps. So the reproducibility is also very important. It's nice that you can produce this algorithm, but being able to share it with others, perhaps reference them in papers, so others might be able to reproduce them, is really important, and it's quite often a big challenge in Earth observation as well. So one of the solutions to these problems is the Copernicus Data Space ecosystem, which is growing to becoming the largest, providing you the immediate access to the largest amount of open and free Earth observation data, and allowing you to download them, visualize them in a browser, but also access to processing clusters to be able to actually do something with this vast amount of data. And to give you an idea, I think today I took this snapshot from the dashboard of the amount of raw Sentinel data is already available within CDSE. We're talking petabytes here, and it's growing by the day. That is quite a lot, and Copernicus Data Space ecosystem already gives you access to a vast amount of data. But then we still face, of course, the problem, how do we want to process all this data? Do we do it locally? Do we download the full Sentinel-2 imagery, cut it up, and continue with this data, or do we grab to something more robust and reproducible? And that is where OpenEO comes into the picture. Now, OpenEO to its core is not linked to CDSE. That's sometimes a confusion I notice with people. OpenEO to its core is an open source API, so it's backend agnostic, that provides users with access to EO data and simplifies the deployment of your processing workflows. You notice here the words scalable and cost-efficient services are also mentioned, and that is really the topic of this webinar, because getting access to these backends with cloud infrastructure, you can already scale up your whole workflow. Now, what does this open source API look like? To computer, it looks a bit like this, JSON. While this one is a pretty simple one, JSONs are typically not very human readable, so we can visualize them as this as well. And actually, this is really the core. We see these data cubes, and we apply processes on them. And that is how we built the recipes, which are called OpenEO process graphs. What we might notice here is we load in some Sentinel-2 data. We give it a certain bounding box, temporal extent, and we request 3 specific bands. And we save that result as a GTIFF. So as a user, you simply have to define what you actually want, how you want it processed, and no longer load in different data formats, load in the large files locally, apologies, cut them up and get only the results you actually need. You're able to define exactly what you want. To give you a bit more as an advanced example, this is kind of the upgraded version of the previous one, where we also load in the scene classification layer. We turn it into a cloud mask, and we reduce the whole temporal dimension we requested into one image, so we get this nice cloud-free composite. And this one will come back later. I'll show you the Python code to produce this one. But so OpenEO is really this formal contract that you create, send it to a backend, and get your results directly. And all the processing happens on the backend. You don't have to see terabytes of data locally. So your internet provider might thank you for that. You can only load in the results you actually need. To give you a quick overview of why OpenAO is so important, and I might fall into repetition a little bit, but it's because it's really important. It's at the core of OpenAO, is it simplifies the data access and processing for multiple observation data sets. It gives you access to scalable and efficient cloud computation without having to set up your own Kubernetes cluster, for example. And it is a standardized system that works across different platforms. So CDSE is one OpenAO backend provider, but there are different other OpenAO options. There's even a OpenAO backend that can run locally on your laptop. So there's quite a lot of alternatives if you don't want to have this backend lock-in, which I think is very important as well. You can focus at the task at hand, not the data engineering. Forget all about the data formats that you need to load in, but really focus on defining how you want everything processed. And lastly, but really at the core of OpenAO is it supports the principles of fair and open science, making sure everything is reproducible, interoperable, as we'll later see also findable and accessible. Now, that is quite a lot of OpenAO. In other webinars or other tutorials, we might zoom in a bit more on what are data cubes, what are processes, and how you make those. But the goal of this webinar is really looking at how can we scale that up. And before I dive into that, I'd like to give you a few examples of projects that have used OpenAO and CDSE to actually produce large maps and scale up their processing workflows. And so the first two I want to mention are World Serial and Land Cover Forest Monitoring. As those projects typically, before starting to process, they would cut up a grid of, let's say, 10 to 20 kilometer grids and do that processing block by block, then put them all back together. Typically, they adhere to these kind of blocks because they're limited by the memory they might have on a virtual machine or on their laptop, the amount of RAM available. So they're really limited to this extent to be able to process at once, and they have to do the stitching afterwards. Now, what we see for these projects when trying to prepare their algorithms for pan-European or even global production is we tested out different extents, and what we found is for World Serial, it's a lot more efficient to process them at a 50 by 50 kilometer scale. And we sent this contract to OpenAO telling, hey, we want this 50 by 50 kilometer square. And then OpenAO handles all the parallelization in itself. It has a whole team of developers here at Vito and across Europe as well that really optimize how we can parallelize this. It uses Spark, a Kubernetes cluster, but you don't need to know a lot of that. It's just that OpenAO already introduces some parallelization, allowing you to scale up your OpenAO jobs one by one. And for LCFM, we did that scale up even further, and we started processing full Sentinel-2 tiles, doing land cover, category, classification. So it's nice to see that we can step away from this limitation where we had to process these 15 by 15 kilometer blocks and really get to do full Sentinel-2 processing at once. Now, the two other projects I mentioned here are Grassland Watch and World Ecosystem Extend Dynamics. And Grassland Watch is a project where I've been involved quite a lot for the past 2 years. And what we see there is we're trying to make this pan-European map, both for land cover classification, grassland type classification, and that's from present day all the way back to 1994. So that's quite a lot of maps, quite a lot of processing blocks we need to handle. And that is where we need to look further than just trying to run it all in a single OpenAO job, but introduce this sort of job manager so we can launch production, step away from it, and do a daily check-in. To give you some visuals on how this processing is actually going. So to the left, we see a map of the different processing blocks that have been processed for Grassland Watch. You see it spans quite nice over Europe. The different holes are because we only focus on processing grasslands, and unfortunately those are not present everywhere. But this gives you a nice overview. It's so much zoomed out that you can't even see the different, the sheer amount of jobs that were managed in a way that we will see later. On the top right, you see an ongoing job manager of World Serial processing the whole of France. The green ones are processed, the blue ones are still running, and I think the yellow one spot is a job that is in the queued status with some gray blocks still to be processed. And on the bottom right, what we see is actually a full global composites, a I think it's an annual median of the Sentinel-1 bands that was produced with OpenEO as well at these very large scales, Sentinel-2 scales, and then stitched together to create this global image, but also used on a Sentinel-2 tile level to train machine learning models, for example, for land classification. So these are very nice 3 examples of how OpenEO was already used in practice. And the reason I really wanted to start with this was I've been telling people about OpenEO for the past 2 years, and the response is often, okay, it's nice in theory, but does it actually work? And here we see some nice examples of large-scale projects having used OpenEO within CDSE to produce these maps. Now, enough of these theory slides, enough of examples. I think it's also important to see how you could reproduce it. And for that, we use 2 community notebooks. There is a link here which will be accessible after the webinar, where you can find them yourselves. And these are Jupyter notebooks showing you how to use the OpenEO Python client to create OpenEO jobs and to really scale them up to create a map of your whole country or even Europe or the whole world. So the first notebook is one on specifically the multi-backend job manager. And this job manager is exactly what will be managing our whole production. So there's 3 components as a user that we need to implement. This is a small snippet from the Python documentation, which contains quite a lot of information, a lot more than I could tell you in this half-hour webinar. So there's 3 components that the multi-backend job manager needs. First of all, the manager itself needs to be initialized, given a directory where it could save all the results. Secondly, we need a job database. And so this is the grids that we need to create, telling the manager how it should split up the work. And then thirdly, we need a start job callback, a function that contains all the logics on how we want the processing to happen, a function that contains the logics on how we want to produce the OpenEO process graph. And so I've put a few snippets from the notebooks in the slides. As you go through them yourself, there's a lot more markdown written down, a lot more information. But I simply wanted to give you a short flow through the notebook. And we start with defining our area of interest. This area is a small area. I think it's 20 by 20 kilometers in the south of Belgium. We define in EPSG in which we want our results, and the tile size, in this case, I want to process them at 10 by 10 kilometer blocks. And once we have that, there's a new function from the OpenEO Python client. It's a bit small on the slides perhaps, but it's clear in the notebook, called split area. And we simply provide them with the area of interest, the tile size that we want, and the projection. And it will give us this geodata frame where the different areas are split up. And as we see to the right, the area of 20 by 20 kilometers has been divided in 4 10 by 10 kilometer blocks. So that is our first part. That's a job database that we need. The next one is defining the function on how we actually want to do the processing. Now, once again, we're focusing on scaling it up. So I won't be going too deep into how to create these process graphs. But I do want to show you this example, as it is an example that's quite often requested, creating cloud-free Sentinel-2 images. And what we see to the left is we unpack our bounds. We load in the scene classification layer from Sentinel-2 using a load collection, and we turn that into a cloud mask using the 2SCL dilation mask. And then to the right, we have, again, loading in Sentinel-2 data, selecting the bands 2, 3, and 4, which are the RGB bands, and we apply the mask to that. So as you see, it's kind of like building with Lego blocks. We built these different data cubes on each other and link them together. And all the way at the end, we tell them, hey, backend, create this job for me, and I want the output format to be a GeoTIFF. So once again, if this is quite fast for you, there is a getting started notebook, which explains every step very in depth, so you can try it out yourself. For now, I'm kind of skipping over this so we can continue on scaling up this workflow. Then the third component we need is the job manager itself. So we simply call the class the multi-backend job manager. The name kind of says it, it allows you to connect to different OpenAO backends and split up your work. We notice, however, in practice that often you want to use one specific backend which provides the right data that you need. In this case, we're connecting to the Copernicus Dataspace ecosystem at openao.dataspace.copernicus.eu. If you actually go to this link in your browser, you will get access to the web editor, which you might recognize a screenshot from later in the presentation. So we created our job database, we created our job manager, our start job function. All that is left to do is do manager.run jobs, provide them all these arguments, and the manager will start running for you. Now, what will we actually do in the backend? We have quite an extensive job manager. It's multi-threaded to make sure that we can send in sufficient jobs at the same time. And you also define your parallel jobs. The default is 2. It will start sending these jobs to the backend and then start polling the status. As soon as a job finishes, the job manager will send in a new job. And this kind of handles how much you're actually sending to the backend. And it handles it in a very nice way, handling all the errors. When your job is finished, it will download the results to your computer so you can work with them later as well. If there might be an error, sometimes unfortunately those happen, those logs will get downloaded as well. And it does all this for you. Now, what is nice about this, let's say you want to process the whole of Belgium, which can be quite a lot of processing blocks, is that you create this job database. You start your job manager on perhaps a virtual machine or on a laptop that you put a note, post it on, please don't close it. And then you can end your workday, have a nice evening, and the next day you open up your manager and you will see how many jobs are being processed already. So that is a quick run through the first notebook. Actually, I had a run at this for the small area in Belgium and created this cloud-free, I think it's 3 months composites somewhere in the south of Belgium, which shows you some nice agricultural fields. But of course, you can do quite a lot more than simply create these cloud-free images. You can do machine learning with OpenAO and manage all these workflows as well. Now, if earlier you thought, well, this explanation on how to create these OpenAO process graphs is going quite fast for me, and might be a bit overwhelming, I'd like to take a step back again and come back to why OpenAO is also very fair, and findable and accessible are 2 core parts of OpenAO as well. And this is where, for example, the Apex algorithm catalog comes into play. And the Apex algorithm catalog is a catalog where users can provide their OpenAO process graphs and share them with the world, share them with the rest, so that they can reuse it. There's no need to reinvent the wheel when other researchers might have already implemented an algorithm that a lot of different people need. I took a quick snapshot of the algorithm catalog, and to the left we see a best available pixel algorithm. To the middle we see biophysical parameters calculation, where you can calculate, for example, the leaf area index or the fraction of observed photosynthetically active radiation, FAPAR in short. And to the right, we see a yet unstable process graph to detect peaks and valleys in time series. These are just 3 examples of potential algorithms that you might simply pick and reuse without having to create OpenAO process graphs yourself. And so we're going to do that for the left one. The best available pixel composite is a composite that selects a single pixel per month and provides you with this pixel. Instead of having to do advanced compositing, it's a really efficient way of creating monthly composites. And if you open the second notebook in the community notebooks, you'll notice that you don't have this very complex start job function definition anymore. We simply load in the process graph URL, my apologies, that you can fetch from the Apex algorithm catalog website and provide that to a process-based job creator. And all that is left is defining which temporal extent you want, once again defining this job database as we've done earlier, and then giving that back to your job manager. And so once again, we can scale up our OpenAO process graphs, but you can actually apply it to algorithms that other people have created. And this is very nice because at this point, we might create an algorithm to detect forests here in Belgium, and we might have funding to do processing overhaul of Belgium. But someone in Germany might think, oh, this might be useful for me as well. Simply take your existing algorithm and scale it up to their area of liking. I've been talking quite a lot about Belgium. So of course I tried it out on Belgium itself. Here I created a job grid. I think I used 10 by 10 kilometer grids to actually produce this best available pixel. You'll see it in the notebook. The notebook contains a bit of a smaller area, but you can provide it with any polygon that you want. And if you run the last cell, you'll notice one difference with the previous notebook as well is that the previous notebook runs synchronously, while here we start the manager in a thread. So it runs in the background, and we can update this visualization while running. And you can get this nice sped up visualization of how the job manager processes your whole area of interest. It might be nice to wake up the next morning and see how far did my manager actually get, and see this nice overview of, okay, I'm already at half of Belgium and still half to go. And that gives you quite this interactive look on how the manager is acting. All right. Of course, as soon as I talk to people about scaling up your workflows, everyone finds it very nice and well. But then I often get the question, now, how much does this cost? And that's why we also should talk about credits. As soon as you try to scale up your processing, cost is always a question if you have to host your own infrastructure or you have to rent cloud infrastructure. Now, I took one job of this best available pixel. I ran it for a whole year for a 20 by 20 kilometer area, and this cost me 8 OpenEO credits. To give you some reference, each month on CSE you can get 10,000 credits for free. And I did a quick calculation of how much area you could actually calculate each month, the best available pixel. And so if you would run this each month for 1 month for a large enough area, you would be able to process 6 million square kilometers just on a free tier without having to pay anything. Of course, you are limited to the 2 job the limit on how many parallel jobs you can run, being 2 for a standard user, but it gives you access to quite a lot of processing from the start. If you want to scale up your algorithm or you're part of a project with processing budgets, of course there are also commercial offerings on CSE to actually being able to scale up and speed up your processing. But if you're interested in that, feel free to contact me afterwards. For now, I recommend try it out yourself, try out to process an area around where you live perhaps, or try to do some change detection using OpenEO on a large area. And I can already tell you, with the free credits, you can do quite a lot of processing yourself while developing the algorithm already. As a last point, I want to mention that there's a very active user community on OpenEO. We have our user forums where you can ask questions, and we try to respond on them within 3 days to the latest, but typically we respond each day. And these questions can range from, hey, I have this OpenEO job that is failing, why is it failing? But also, if you don't really know where to start, just explain what you're trying to do, and we might point you to the right examples where it already has been done before. And so with that, I'd like to finish my parts, and we can move to the Q&A. But I'd like to thank you from the whole consortium for being interested in this webinar, and I hope to be able to see some examples of how you're actually using OpenEO and how you're scaling up your processing from an image of your house to perhaps the whole country. Thank you for your attention.
Thank you very much, Victor, for an excellent presentation. Very interesting. I think what was particularly interesting was how you went through first the conceptual side of cloud-native EO processing, and then went to the concrete examples of operational processing at scale, and then you gave us the workbook. So I think it was a very good progression. So super interesting. So right now we will go through the Q&A. I do have a couple of questions. Looks like 3 questions in the Q&A that I'll read through. Just remember that you need to, don't raise your hand, but go ahead and put your questions directly in the Q&A tab. I'll start with the top. We have a question from Jeff Smith. He's asking, can you set up a job that waits for Sentinel-2 acquisitions and then runs the processing on your area of interest, reports, and then goes back to waiting? So I think before the data is available, basically.
Yeah, so that is something that has not yet been implemented in OpenEO. In CDAZ, typically data is available after, I think it's 24 hours. And in practice, how we do this, because we have quite some workflows like that, providing near real-time data, is we set up some sort of NiFi or Airflow that triggers each day and then launches the OpenEO jobs. So unfortunately, no, there's not automatic processing yet of the newest data, but you can schedule in these OpenEO jobs yourself as well.
Okay. And our next question comes from Lubin Branzalov. And he's asking, let's say we have our own algorithms which are private. How do we create a process graph JSON file that we can reuse to be compatible with OpenEO?
So there's two approaches to this. It's fully OpenEO native, where you combine the different processes available in OpenEO. And I'd advise using the OpenEO Python client. So it's Python Pydantic, and reproduce your algorithm. But there's also a step in between where you can provide your user-defined functions, which is a Python script, to OpenEO. And you simply have to define your input data to that script, and you can use the output data as well. For both cases, there is quite a lot of documentation, but I recommend looking at the community notebooks, as these give you a very nice overview of how OpenEO should kind of be developed. They're developed by experts who've done quite a lot of different projects. So I really recommend going through these notebooks and seeing if you can find anything that looks like your own algorithm, so you can adjust it a bit.
Yeah, that's right. There are lots of resources which you highlighted in your presentation available, as well as you're able to ask questions, right?
Yeah.
Good. And just as a follow-up question, Lubin wanted to know about enterprise collaboration on big workflows and what the pricing is like for commercial enterprises, if there's a difference or.
I'm not the expert on the pricing. I'm more of a data engineer from my side, so give me the data and the optimization. But there's a nice overview of this on the CDAZ page with contact information. And for larger projects, as soon as we reach a certain level, it's always best to go into a discussion of what is actually needed. Basic support and form support will always be provided for any question that you pose. For very complex questions, of course, we might need to schedule in a meeting and see if we can help you that way.
Thanks, Victor. So our next question is from Luca Maffanini, who wants to know if you can also inspect the code inside already existing algorithms published as OpenEO workflows. So in case he wants to use an existing one but change the parameters or parts of the logic.
Yes, so every algorithm that's published on the Apex algorithm catalog is also linked to a public GitHub containing all the different JSONs. And for a lot of these processes, also the Python script that was used to generate this OpenEO process graph. So it's all transparent, and you can inspect them yourself or use them as inspiration and adjust them to your needs. Yeah, so you should be able to inspect them.
Thank you. The next question is from Gumede Bogenkosi. Which Sentinel satellite is best for vessel observation at sea using OpenEO?
I'm not a thematic expert on this. What I would recommend is look at the different resolutions. Of course, Sentinel-2 has lots of 10-meter resolution bands. So it's really also dependent on which kind of vessel, how large is it, and what are you trying to detect. It's also important to consider time frames and the amount of acquisitions per day to be able to detect them. But I'm not really a thematic expert on this. Unfortunately, I wish I could give you a straight answer to that.
And our next question is from Max. He's asking, well, he says that his understanding is that a key idea behind OpenEO is backend agnosticism, so that the same workflow can run across different backends without major code changes. But he has not seen examples demonstrating this in practice. Is backend portability a core goal of OpenEO, or are backend specific adaptations still generally required?
Yes, and it's indeed something. Of course, you have a first adapter, and I think both Terrascope here running in Belgium at Vito and CDSE, they run with the same backend, so they have been the first to develop this as a really cloud-native OpenEO backend. There are some implementations even from Google, but as well from Sentinel Hub that give you OpenEO access. But lately, there's also been a OpenEO TI tiler implementation, being able to run on the fly for very quick calculations. There is a OpenEO Dask implementation, which you should be able to run locally on your laptop. So there are all these different OpenEO implementations being developed more and more. And I think even since last week, OpenEO was adapted as an official OGC community standard. So I'm hoping with that it's now an officially community standard on that level as well, that more of these backends will pop up. The reason that it's very important, of course, as a CDSE representative, I can highly advise you to use CDSE, but there are some data sets that we don't yet have. And of course, we want users to have this reliability of knowing if one backend drops, we're not stuck with all these algorithms that we developed. So being able to promise this backend agnostic open source API to users is in that way very important to us as well.
Thank you, Victor. So running through the next, there are quite a few questions. So any questions that we don't get to, we will try to respond to, of course, by email. Yeah. But he is asking what kind of operations are possible to run on the back end? Examples, aggregates, reduce, map. What about ML model inference? What about atmospheric corrections other than send to core?
Yeah. Great question. So I think there's quite a lot of things possible with OpenEO. In the examples we saw from a very high level already some temporal reductions, but we can also do aggregations over spatial areas. Let's say you're a farmer, you have a field, but you simply want one value for your whole field. You're not interested in maps, but rather graphs. Although I'm yet to meet a farmer that is interested in graphs. So these aggregations and these reductions are definitely possible with OpenEO, but these machine learning applications are also possible with the previously mentioned user-defined functions. You're able to run TensorFlow, PyTorch, or ONNX, which are Open Neural Network Exchange models, on your OpenEO workflows. That is actually being used in World Serial and Grassland Watch, where classification is being done with these neural networks. So it is definitely possible. Currently, we are limited to running Python code. It's Python 3.11, so it's quite performance. Yeah, you can do quite a lot with it. And I might repeat this for different answers as well. I really advise you to have a look at community notebooks. There's one on parcel delineation and ONNX machine learning application that might point you into the right direction there.
Thank you, Victor. And yes, we will provide links as well after the webinar for everyone who's interested. The next question is asking about scalability. So what is the scalability in terms of integrating external data like the cloud-free Landsat GLAD data archive for the purpose of ML processing?
So the GLAD dataset has actually been integrated in CDSE. So it has the name Landsat Bimonthly. So you can already directly access this dataset within OpenEO on CDSE. It has been used for Grassland Watch to produce the maps all the way back to 1997, because that's the range of the data. But if you want to bring any other data into OpenEO, OpenEO relies heavily on stack usage. So if you have a stack collection that is publicly available that points to your data and OpenEO is able to access this data, you're actually able to bring your own data into OpenEO. The scalability depends a lot on your data. If you have cloud optimized geotiffs, then OpenAO can work with it quite well, as well as NetCDFs, and we're developing more and more support for ZAR. Of course, it is quite a big specification, so developments are still ongoing there. And what we see is these large projects typically need their own specific data sets that they might pre-process. So these examples I gave earlier are already using external data using stack collections.
Thank you, Victor. So I'll keep going through the questions. So our next question is asking about data size. What data size is limited to use as free? So about data limits.
Yeah. So the main limitations are the number of concurrent OpenAO jobs and the credits that we provide you. So you get 10,000 credits each month, and this is going to be the main limitation of how much you can run with a free tier account. But I'd say try it out a bit. You'll notice that these credits are quite a lot already. So unless you're doing global productions, these might already suffice for your use case.
Thank you. And the next question, so what are the differences between warning, critical, and healthy status of data? Are the datasets resampled, especially for HLS, or consequent products, as some datasets are overly cloudy at their actual sources?
Yes, so you might be referring to the stable and unstable we saw in the presentation, but those are specifically for the algorithms. So that means if an algorithm has been validated sufficiently, it will get a stable stamp. If it is still under development, it will typically be unstable. And we have integration testing for that. As for the data sets, I recommend you read the actual information from each data set. You can fetch that through OpenAO or on the Copernicus website as well. Of course, having analysis-ready data is very important. So Sentinel-2 Level 2A data has quite a lot of clouds. That is where these algorithms like best available pixel come into play as perhaps a starting block for your OpenAO process graph. So you know for sure that you have these cloud-free monthly images that you can build further on.
Thank you, Victor. So I'm looking at the Q&A. I don't think I see other questions. So remember, instead of raising your hand, make sure to put your questions directly into the Q&A tab and not in the chat, because I'm not checking the chat, so I don't see other questions. I did have a question for you, though, Victor, for those users that might be joining that are not used to these cloud-native workflows, might do more traditional local processing. What do you think for them might be the biggest conceptual shift when moving to these cloud-native approaches?
So perhaps the biggest shift in thinking is that until you actually send in a full processing flow, you don't have any data locally on your laptop yet. And this poses some challenges for debugging. Typically, users might want to try something else, and see the results directly. Whereas with OpenAO, you have to define the recipe, as I call it, send it to the backend to wait for the result and inspect that. So in terms of development, this can set you back a little bit. However, if you look up a bit on synchronous and asynchronous processing, this process can already be sped up quite a lot. But this concept of until I actually send in a job, start it, and fetch the results, no data is yet on my laptop, can be a bit confusing and can be kind of groundbreaking in terms of how your debugging workflow would typically run. That's also why OpenAO backend implementations, such as the one using TI-Tiler, are very important because those are a bit more responsive, so you can do some prototyping. And then as soon as you're ready to scale up, you can send these existing process graphs to a cloud-native backend.
Okay, so it's really users getting used to this new way of working, not really being able to do the testing locally. But then, as you said, if you're working with really big, lots of data with big workflows, it's maybe not always possible to do the testing locally yourself, right? You mentioned at the
Yeah,
beginning. Yeah.
because once again, you don't need to download the full products on your laptop first. So you're able to use all these existing data sets in the cloud.
Yeah. And just after your presentation, I mentioned that I really liked the progression in your presentation, going from the conceptual to the concrete examples. And you showed these workflows that evolved from small tiled approaches to larger operational production scales, which is very good for the potential users or users to see. But of course, there might be technical or organizational challenges. And as you have a lot of experience in working with cloud native workflows, with these processes, maybe you can share some of those challenges that you've encountered in your experience and how you've overcome those, because that
Yeah.
might be a question that our users have.
So typically, of course, there's quite a lot of performance optimization if you're looking at running any workflow at a global scale. We find quite a lot of small improvements. And I think for especially the first year I worked on OpenAO, these optimizations were really the main part of my job. And we have this project defining this OpenAO workflow, sending it to the backend and looking at, oh, this costs more than I expected. And so what we've done is we've implemented quite a lot of improvements. But what is nice is that every improvement we see for one project influences all the other projects using OpenAO as well. And what we end up is with this backend that is very generic and can handle all these different kinds of process graphs pretty efficiently. And to the day, we're still receiving these new requests, these new workflows. And each time we might find a new performance optimization, but yeah, we keep on working on this. Each time we find a bug or we find something, then we resolve it for all the other projects using OpenAO as well. But so these performance optimizations are really a very big first challenge. But we're seeing that it's maturing more and more. And that's why I really wanted to focus this webinar on showing these examples of projects that have already used OpenAO to produce these global maps. Because they can be used as an example of how OpenAO is getting more and more mature for these real life examples.
Thank you, Victor. And we have another new question asking about atmospheric corrections incorporated in the future. So Konstantinos wants to know if there will be corrections such as Acolyte Polymer or C2RCC variants. This wasn't discussed, he says.
Yes, so indeed, it is hard to tackle all the different requests. There are very specific workflows that need to be implemented. And at first we have to see how we can do this, but there's a new sort of processing that we're also working on using CWL or Common Workflow Language, I think. Don't hold me accountable for that one. But it allows you to write and run your own Docker images on Earth observation data. And this allows you to port existing atmospheric correction algorithms written, for example, in C or anything, run them on the OpenAO cluster, get their output, and then proceed to work with standard OpenAO workflows. And so this is still quite experimental, but they're investing quite a lot of development time into making sure we can reuse all these efficient algorithms that have been developed over the past decades, and we don't have to reinvent the wheel there as well. So in short, is it going to be OpenAO native? Probably not, but there is this way of running these Docker images, these custom scripts, to gain access to all the different types of atmospheric correction.
Yeah, and I think this brings us back to another point that you had, which is that things are rapidly evolving.
Yeah.
This is an ecosystem that is growing as we speak and becoming more and more operationally usable and valid as time goes on.
Yeah.
So we have another question here in the chat asking about what the main advantages are of using OpenAO over traditional Google Earth Engine workflows for scalable geospatial analysis?
Yes, and that's a very nice question, because I think a lot of the researchers already know GEE, and they were kind of the first. But then what we noticed in the past year or 2 years is that they're getting more and more commercial, and they're upping their prices. They might have this feeling of monopoly, but here we have an alternative, which is open source, which is Europe backed, and even the full OpenIO backend implementation is open source. So we have these free tiers with quite a lot of processing already available, and our goal is really to give access to users to this vast amount of remote sensing data. I mentioned it tons of times. These 10,000 credits are really a lot. You can already do quite a lot with it, and our focus is not to make profits on this. It's really giving the community access to these remote sensing workflows. So that's, I think, a big distinction with Google Earth Engine. Hopefully that can give you a bit more of certainty for the future as well. Not developing this workflow and then seeing the cost double over the next years, but having this open source alternative out there.
Yeah, yeah, and this is another big advantage of the Copernicus ecosystem in general, right? Is open and free data for the most part, and really being there for the users and to serve the users.
Yeah.
We have a couple of questions about the presentation. We will be sharing it. I think we have time for one final question. And he is asking, is it possible to link OpenEO to local scripts, or do I have to download OpenEO products first to use them for R-based analysis? So using R-based analysis with OpenEO.
Very good question. I think the R question versus the Python question is one I receive sometimes on conferences as well. For now, we don't have R support for user-defined functions, unfortunately. It's unsure to see if this will come on a roadmap, at least for the near future. We're focusing on these CWL workflows, which could be used for R. But our main focus is still remaining OpenEO native, and we allow this access to Python code to unlock the potential for machine learning. I think a lot of the statistical analyzation you might want to do can either be implemented in OpenEO native algorithms. There's some algorithms doing that on Apex as well. But then you could pre-process the data on OpenEO, do some large-scale aggregations already, and do the final statistical analyzations locally on your computer. But yeah, in short, unfortunately, we have no user-defined function R integration yet, and it's not on the nearby timeline, as to my knowledge.
Thank you very much, Victor. So I think that is kind of the end of the questions. I don't see other ones. And I think we've addressed them all. Any questions that you might have that we missed, we'll go through and we'll try to answer them the best that we can. Also note that the presentation will be made available to you, and also this has been recorded, this session, and will be available on YouTube. So I think at this time I'd like to go ahead and close the session. I'd like to thank Victor very much for taking the time to come and give us really an excellent presentation on scaling workflows in OpenEO, the advantages, really taking us through step by step, starting from the conceptual all the way to the practical, and giving us some tools to start if you haven't done this before. So thank you very much for joining us today and taking the time, Victor.
And thanks everyone for your attention and remain even through the Q&A. Was some very interesting questions, and I hope to see some examples or some questions perhaps from you on the OpenEO forum as well.
All right. So thank you very much, everyone, and we hope to see you in the next webinar.